In April 1945, when the Allied armies crossed the borders of the Third Reich, they did not find merely a defeated country. They found laboratories hidden beneath churches, factories buried in the heart of mountains, nuclear reactors on the verge of becoming operational, and archives describing projects that the world would take decades to fully understand. What Germany had secretly built over 12 years of regime had no precedent in modern military history. Some of these discoveries were purely technological: submarines designed to remain underwater for extended periods, rockets that had brushed the edge of outer space, aircraft without fuselages that anticipated the shapes of 21st century stealth bombers. Others were of a darker nature: underground factories where thousands of prisoners assembled precision weapons until they died of exhaustion, financial espionage operations capable of destabilizing entire economies, and a nuclear program that came closer to success than the world was willing to admit for a long time. The Allies knew they had to act quickly. Technical intelligence was a resource the Soviets were also urgently seeking. Specialized missions such as Operation Alsos, the British T-Force, and units of the Joint Intelligence Objectives Agency combed through Germany with lists of targets, facilities, documents, and scientists identified by name. What they found in those weeks of April and May 1945 would shape the architecture of the post-war world. The space race, the Cold War, the nuclear balance, and modern submarine warfare doctrine were largely born from those discoveries. What follows is a reconstruction of 15 of those findings. Some changed the war without arriving in time to win it. Others left wounds that would take decades to heal, some still open. All, without exception, reveal the scale of what the Third Reich built in secret and what the world inherited when that regime fell. The Type 21 submarine and the origin of modern submarine warfare. On May 4, 1945, the submarine U-2511 was navigating submerged off the coast of Norway. It was one of the first operational submarines of the most advanced type ever built by the Kriegsmarine, the Type 21. Its commander, Captain Lieutenant Adalbert Schnee, acoustically detected a formation of British cruisers while remaining at deep submergence. He executed a full approach, positioned the submarine at an attack angle, calculated the firing solution using automated fire control systems, and when he could have launched torpedoes with an extraordinarily high probability of success, he held back. Hours later, the order to surrender arrived. Germany had capitulated. Schnee surfaced, raised a white flag, and set course for the port of Bergen. It was the final operational act of a submarine that represented an entirely new form of naval warfare. When the Allies inspected the U-2511 and the other Type 21 submarines captured intact, the scale of the technological leap left them speechless. This was not an incremental improvement over previous models. The Type 21 had been designed from the ground up to operate permanently underwater. The fundamental difference lay in its propulsion. Submarines of the Second World War were, in essence, surface vessels with a temporary ability to submerge. They spent most of their time on the surface using diesel engines and only dived during attacks or to evade threats. Underwater, they relied on low-power electric motors and limited batteries that restricted their endurance to a few hours. The Type 21 completely reversed this logic. Its batteries had 3 times the capacity of earlier models. Its electric motors were both quiet and powerful, capable of maintaining speeds of nearly 10 knots while submerged for entire days. The integrated snorkel reinforced this advantage. The device allowed the submarine to draw in air from the surface while remaining at periscope depth, recharging its batteries without needing to fully surface. The Type 21 incorporated it with automatic valves and improved ventilation systems that drastically reduced visual and radar exposure, a submarine that barely needed to reveal itself to the outside world. The hull completed the revolution. Instead of a shape optimized for surface navigation, the Type 21 had a nearly perfect hydrodynamic profile, resembling a teardrop designed to minimize resistance underwater. Thanks to this, it could reach speeds of up to 17 knots in short submerged bursts, faster than many Allied surface escorts. It could also dive below 250 meters, beyond the effective range of Allied depth charges, which were calibrated for detonations in shallower waters. Its armament reflected this new approach. 6 bow torpedo tubes with a hydraulic reloading system allowed it to fire a full salvo and reload in less than 20 minutes. In earlier submarines, that process could take more than an hour. With 23 torpedoes on board, the Type 21 could carry out multiple attacks without returning to base. Its fire control system was equally advanced. Electromechanical computers automatically calculated firing solutions, taking into account the target's speed, course, and distance, as well as the submarine's own movements. Its passive sonar was extraordinarily sensitive, capable of detecting ships dozens of kilometers away under favorable conditions. But what impressed Allied engineers most was its method of construction. The Type 21 was the first submarine built using large-scale modular production. Instead of being constructed continuously in a single shipyard, it was assembled in independent sections in factories scattered across Germany. These sections were transported by rail and canal to final assembly yards, where they were welded together in a matter of weeks. The goal was to accelerate production and reduce vulnerability to Allied bombing. The theoretical construction time was reduced to less than 3 months, but speed came at a cost. Many units suffered from welding defects, electrical problems, and alignment failures. Between 1944 and 1945, 118 Type 21 submarines were built, but only 4 completed operational patrols, and only 1 came close to simulating a real attack. Even so, post-war Allied technical reports were unequivocal. If Germany had managed to deploy several dozen operational Type 21 submarines in 1944, when it still controlled bases in France and Norway, the Battle of the Atlantic might have had a very different outcome. Allied anti-submarine tactics, based on radar, patrol aviation, and fast escorts, were effective against submarines that needed to surface frequently. They were not designed to counter a submarine capable of remaining submerged for days, moving faster underwater and attacking from depths that were difficult to reach. The Allies acted quickly. The captured submarines were subjected to exhaustive testing. The United States developed the Guppy program, which transformed existing submarines by applying the principles of the Type 21. More hydrodynamic hulls, expanded batteries, and the removal of superfluous elements to improve submerged performance. The Soviet Union captured several intact Type 21 submarines and used them as the design basis for a class of submarines produced in large numbers. During the 1950s, these submarines patrolled seas around the world and formed the backbone of the Soviet fleet. The ultimate legacy of the Type 21 materialized with the arrival of nuclear submarines. When the first nuclear-powered models were designed, the concept was clear. A submarine had to be a permanently submerged platform, not a vessel that dived only occasionally. The hydrodynamic hull, the priority given to underwater navigation, and the automation of systems all stemmed directly from the German design. The U-2511 was scrapped years after the war. But the shape that naval warfare took from that point forward still bears its imprint. The hidden reactor of Hygalok and Nazi nuclear capabilities. In April 1945, American units of the scientific mission Operation Alsos arrived in the small town of Hygalok in southwestern Germany. Beneath a church carved into the rock, they discovered an experimental installation that had remained hidden throughout the war. Inside an artificial cavern, they found an incomplete nuclear reactor, the last German attempt to achieve a controlled nuclear reaction. The reactor, designated B8, consisted of a cylindrical structure containing hundreds of cubes of metallic uranium suspended BTVKH, a tank filled with heavy water. The objective was to trigger a self-sustaining chain reaction in which the neutrons released by uranium fission would continuously generate new fissions. Reaching this state, known as criticality, was the essential step both for producing nuclear energy and for developing atomic weapons. The German nuclear program had begun in 1939 following the discovery of nuclear fission in Berlin. Leading physicists, including Werner Heisenberg of the University of Leipzig, took part in the initial theoretical studies. However, the project never received a level of strategic priority comparable to that of the V-2 rocket program. Resources were limited, and the work remained fragmented across different institutions, lacking the centralized structure that characterized the American Manhattan Project. One of the main problems was the choice of moderator, the material required to slow down neutrons without absorbing them. Germany ruled out graphite due to impurities that absorbed neutrons in the available samples and instead chose heavy water. This substance was only produced in significant quantities at a plant in Vemork, Norway. The facility became the target of repeated sabotage by the Norwegian resistance and Allied bombing, drastically reducing the available supply. The shortage of heavy water prevented the experimental reactors from reaching the required critical mass. The Hygalok reactor came close, but it failed to sustain the reaction. Later calculations indicated that it would have required significantly larger quantities of uranium and moderator materials, resources that Germany was no longer capable of producing. In 1945, when the Operation Alsos mission captured the installation, it confiscated all nuclear material and associated documentation. The leading scientists were arrested and taken to England, where they were kept under surveillance. Secret recordings of their conversations revealed that they lacked understanding of key aspects of a functional nuclear bomb design, confirming that the German program was far from producing a weapon. Allied reports concluded that the German failure resulted from a combination of factors: scarcity of resources, constant disruptions, miscalculations, and the absence of a centralized structure. Samuel Gaudsmit, scientific director of the Alsos mission, later wrote that the captured German scientists reacted to the news of the atomic bombing of Hiroshima in August 1945 with a mix of disbelief and mortification. They could not believe that the Americans had succeeded where they had failed. The Hygalok reactor was dismantled. The nuclear material was sent to the United States for analysis and reuse. Today, the site functions as a museum, and inside the original cave one can see a replica of the reactor structure, a haunting relic of a possibility that came very close to becoming reality. The Horton HO229, the silhouette the future would recognize as its own. In April 1945, American troops of the Ninth Army occupied the facilities of the Gotha wagon fabric factory in Friedrichroda, central Germany. Among damaged buildings and abandoned machinery, technical intelligence teams found something that did not fit into any known category. It had no conventional fuselage or tail. It was a massive delta-shaped wing made of plywood and steel tubing with two jet engines embedded within it. It was the Horton HO229, the world's first jet-powered flying wing aircraft. Behind the design were the brothers Reimar Horton and Walter Horton, two pilots and engineers obsessed with aerodynamic efficiency since the 1930s. Their idea was radical but simple. The fuselage and tail generate drag without providing real lift. If the entire aircraft were a wing, drag would be reduced and performance increased. For years, they had tested this theory with gliders, refining shapes and control systems. In 1943, that obsession aligned with an increasingly desperate strategic need of the Luftwaffe. Hermann Göring had set a specific requirement: 1,000 kilometers per hour of speed, 1,000 kilometers of range, and 1,000 kilograms of payload. It was a direct response to Allied bombing over Germany. The Horton brothers proposed an extreme solution: a jet-powered flying wing with no fuselage, no tail, and a minimal silhouette. The HO229 had a wingspan of nearly 17 meters and a pronounced sweep angle. Its structure combined a central steel tube framework with a glued plywood skin. There were no conventional control surfaces. The aircraft was controlled through elevons, movable surfaces on the trailing edge that combined the functions of ailerons and elevators. It was a complex system, but it allowed the aircraft to be controlled without the need for a tail. The selected engines were two BMW 003 turbojets mounted BTVKH the wing, near the center. Each provided approximately 800 kilograms of thrust. In theory, the HO229 could reach speeds close to 1,000 kilometers per hour, comparable to the Me-262, but with a considerably cleaner aerodynamic form. Decades later, an unsettling question emerged. During the restoration of the only surviving HO229, carried out by the Smithsonian Institution, it was discovered that the wooden skin had been impregnated with a mixture of sawdust, charcoal, and adhesive. Later analysis showed that the charcoal had radar-absorbing properties. This raised an unavoidable question. Had the Horton brothers attempted to reduce radar detection before the concept of stealth aviation formally existed? Raymar Horton was questioned several times about this point in his later years. His answers were never entirely clear. At times, he claimed the mixture was only used to bond the layers of wood. At others, he admitted they had intuitively considered radar detection. In 2009, modern engineers built a replica of the HO229 and tested it using radar systems equivalent to those employed by the British in 1945. The results indicated that its detection range would have been significantly reduced, down to roughly 1/5. It was not invisibility, but it did represent a real advantage. In the context of aerial warfare, a few extra seconds could mean the difference between being intercepted or not. Only 3 prototypes were built. The first was an unpowered glider used to verify stability and control. The second was the first jet-powered model and flew in early 1945. Flight reports indicated that it was fast and stable, although it required precise handling. During its third flight, one of the engines failed. The pilot attempted to return on a single engine, lost control during the approach, and was killed in the crash. The third prototype was incomplete when American forces arrived. It was carefully dismantled, packed, and sent to the United States along with its plans and documentation. For decades, it remained in storage, largely forgotten, until a slow restoration process began. The effort was complex and painstaking. Many parts were damaged or had never been installed. Conservators worked from photographs, original plans, and recovered fragments. Over time, the HO229 began to attract the attention of engineers from modern aerospace companies. The similarities to contemporary stealth bombers were evident: a flying wing, integrated engines, absence of vertical surfaces, and a clean silhouette. The differences were equally clear. The HO229 was not designed using advanced radar calculations or modern composite materials. Its stealth characteristics were, to a large extent, an indirect consequence of its pursuit of aerodynamic efficiency. The HO229 never entered combat. It never dropped a bomb, nor was it tested under real wartime conditions. Yet it represents an extreme point of experimentation, where the pressures of conflict pushed engineers to explore radical solutions. It demonstrates that even in the final months of the war, Germany was still producing ideas that the world would take decades to fully realize. The Vampire and the technological dominance of the night. In the final months of the war, Germany achieved something no other army had accomplished, enabling individual soldiers to see and fire accurately in total darkness. This was not based on flares, searchlights, or artificial battlefield illumination, but on a fully operational portable infrared night vision system. The Zielgerät 1229, known as Vampir, represented the first successful attempt to turn the night into a technological advantage. The system was designed to be used with the STG-44 assault rifle and consisted of 3 main components functioning as a single unit. An infrared projector mounted on the weapon emitted light invisible to the human eye. A sight with an image converter tube captured the reflected light and transformed it into a visible image. A high-voltage battery carried in a backpack powered the entire system. The result was striking. The soldier could see enemies in complete darkness while remaining invisible to anyone without the equipment. The physical principle itself was not new. Since the 19th century, it had been known that radiation existed beyond the visible spectrum. The challenge lay in turning that knowledge into a portable, durable, and reliable device suitable for combat conditions. The key component was the image converter tube, an extraordinarily complex technology for its time. The tube used a photocathode sensitive to near-infrared radiation which, when stimulated, released electrons. These electrons were accelerated and projected onto a phosphor screen, creating a visible image in greenish tones. The infrared projector functioned like an invisible flashlight. It used a tungsten lamp with a special filter that blocked visible light while allowing infrared radiation to pass through. Although the beam could not be seen with the naked eye, it illuminated the surroundings sufficiently for the image converter tube to detect it. The complete system was bulky and heavy. It weighed around 16 kilograms, with the battery backpack alone exceeding 9 kilograms. Battery life was limited to between 4 and 5 hours of continuous use. Even so, in specific situations, it offered an absolute tactical advantage. In a nighttime ambush, a soldier equipped with the Vampir could detect, aim, and fire at an opponent before the latter even realized he was being observed. Germany produced around 500 units between 1944 and 1945. It was not a mass deployment, but a selective one. Records indicate they were assigned to elite units, mainly on the Eastern Front and in the defense of the Rhine. For Allied soldiers who encountered these units, the psychological effect was profound, receiving accurate fire from total darkness with no apparent explanation. However, the system had clear limitations. Image quality degraded rapidly with distance and environmental conditions. Beyond about 150 meters, clarity dropped significantly. In addition, the infrared projector had a critical weakness. It was invisible only to those without a similar system. If the enemy also possessed infrared vision, the beam would immediately reveal the shooter's position. This made the Vampir an asymmetrical advantage, powerful only as long as the opponent lacked equivalent technology. The Allies captured several intact systems and analyzed them immediately. Technical reports acknowledged their conceptual effectiveness, but also highlighted logistical challenges. The weight, fragility of electronic components, and dependence on batteries made large-scale deployment impractical with 1945 technology. The message, however, was unmistakable. Night combat had entered a new phase. After the war, both the United States and the Soviet Union invested heavily in night vision technology. Later generations improved sensitivity, endurance, and portability, but the fundamental principle remained the same: transforming the invisible into the visible through electronics. The Vampir did not change the course of the war, but it definitively opened the night as a technological domain. The V2, the weapon that could not be stopped. On September 8, 1944, at 6:43 in the evening, residents of Chiswick, a quiet residential district in West London, heard a brutal explosion that seemed to come from nowhere. No sirens had sounded, no aircraft had flown overhead. On Staveley Road, a crater nearly 10 meters wide suddenly appeared, killing 3 people instantly. 16 seconds later, another detonation shook Epping in the northeast of the capital. British authorities attributed both incidents to gas explosions. That was not true. That afternoon marked the operational debut of the most advanced weapon of the entire Second World War, the German A-4 ballistic missile, known as the V2. Unlike conventional bombing, the V2 could not be seen, heard, or intercepted. There was no warning. Impact arrived before the sound. For civilians, the attack was incomprehensible, almost supernatural. For Allied commanders, the meaning was immediate and alarming. Germany had crossed an entirely new technological threshold. For the first time, a weapon could leave the atmosphere, re-enter at supersonic speed, and destroy a target with no possibility of defense. The rocket stood 14 meters tall and weighed nearly 13 tons at launch. It used a liquid fuel engine powered by a mixture of ethanol and liquid oxygen, an extremely unstable but highly powerful combination. For 65 seconds, that engine generated 25 tons of thrust, accelerating the projectile to speeds above 5,700 kilometers per hour. It reached altitudes close to 90 kilometers, brushing the edge of space, before beginning its ballistic descent toward its target. No existing defense in 1944 could counter such an attack profile. The V2 used gyroscopes to maintain orientation and an accelerometer to measure velocity during ascent. When the system calculated that the planned range had been reached, it automatically cut the engine. It did not rely on radio or external control, making it immune to jamming. Between September 1944 and March 1945, Germany launched more than 3,000 V2 rockets. Approximately 1,400 struck England, most of them in London. A total of 2,754 people were killed and more than 6,500 were seriously injured. Another 1,600 fell on Antwerp, the main Allied supply port in Belgium, causing more than 7,000 military and civilian casualties. The last V2 to hit British soil landed on March 27, 1945, killing a woman named Ivy Millichamp. She was the final victim of a weapon that could not be stopped. When the Allies entered Peenemünde, the testing center on the Baltic coast, and the underground factories of the Harz Massif, they discovered something even more unsettling than the technical sophistication. The V2 program was not experimental, it was fully industrialized. There were assembly lines, detailed manuals, mobile launch systems, and a complex logistical network that included special trains, hydraulic platforms, and equipment capable of handling liquid oxygen in field conditions. Germany had managed to mass-produce ballistic missiles under constant bombardment. The capture of this technology became an urgent operation. In April 1945, Major Robert Staver coordinated the systematic evacuation of components, blueprints, and key personnel from the German program. Werner von Braun, the technical director of the V2, had fled south with his team and tons of documentation, which they buried in an abandoned mine. On May 2nd, he deliberately surrendered to American forces, convinced that his future would be more favorable under their custody. The American response was immediate. Before the region fell under Soviet control, more than 100 complete or partially assembled rockets were recovered from underground facilities. The components were shipped to Antwerp, loaded onto transport vessels and sent to the United States. At the same time, 127 German scientists and engineers were taken first to Texas and then to New Mexico, where they continued their work under military supervision. The first American V2 launch took place on April 16, 1946. The rocket veered off course and crashed, but each test provided crucial data. Soon, scientific instruments replaced explosives to study the upper atmosphere, cosmic radiation, and thermal structure at altitudes never before reached. Within a few years, these experiments transformed knowledge of Earth's environment and laid the foundations for space exploration. The rocket that launched America's first satellite and the heavy-lift launcher that carried humans to the moon descended from the same technical lineage that began at Peenemünde. The Soviets, although arriving later, also capitalized on that legacy. They reconstructed the rocket almost piece by piece and transformed it into the first intercontinental ballistic missile and the vehicle that inaugurated the space age. The V2 did not decide the war, but it defined the post-war world. As ME262, the end of the propeller era. On March 25, 1945, an American P-47 Thunderbolt pilot flying over Bavaria saw something that did not correspond to any known aircraft. A German machine passed him at a speed impossible for any propeller-driven fighter. There were no visible propellers, no radial engines, only two tubes under the wings emitting a bluish glow. The pilot attempted to turn and pursue it, but the aircraft had already vanished into the distance. Without knowing it, he had just encountered the Messerschmitt ME262, the world's first operational jet fighter. When American forces captured the Lechfeld Air Base in April 1945, they found dozens of Me-262s scattered among hangars damaged by bombing raids. Some were complete, others partially assembled, others abandoned for lack of fuel. Allied pilots and engineers inspecting them immediately understood that this was not an incremental improvement, it was a qualitative leap. The difference between a piston-engine fighter and the Me-262 was comparable to that between a World War I biplane and a modern late 1930s fighter. The Me-262 could reach speeds of around 870 kilometers per hour, nearly 200 kilometers per hour faster than the P-51 Mustang, the fastest Allied fighter in service. It was armed with four 30mm cannons, capable of destroying a heavy bomber with only a few hits. Its aerodynamic design, with moderately swept wings, reduced drag at high speed and anticipated principles that would later become standard in jet aviation. The project had begun in 1938, when Germany still expected a short war. Messerschmitt engineers designed the aircraft around turbojet engines that did not yet exist in reliable form. Early prototypes relied on experimental turbojets that frequently failed. Turbines overheated, materials could not withstand thermal stress, and fuel consumption was extreme. For years, the airframe was ready before a suitable engine existed. It was not until 1942 that a functional engine became available, the Junkers Jumo 004. This engine provided sufficient thrust, but at a high cost. Its operational life was extremely short. Heat-resistant alloys required strategic materials that Germany could no longer obtain in sufficient quantities. As a compromise, lower-grade metals were used, causing the engines to wear out after only a few hours of flight. In 1943, Adolf Hitler ordered that the Me-262 be developed as a fast bomber, not as an interceptor. His idea was to use its speed to strike Allied targets without the possibility of interception. Technically feasible, this decision delayed its introduction as a fighter by crucial months. By the time it was finally allowed to operate as an interceptor, the lost time could no longer be recovered. The Me-262 entered operational service in the summer of 1944 with experimental units. In combat, its impact was immediate. Against Allied bombers, it was devastating. Escort fighters could not catch it in level flight. Defensive gunners had barely any time to react. A Me-262 pilot could attack, fire a short burst, and pull away before the enemy could respond. But structural problems persisted. The engines required extremely careful handling. Abrupt throttle movements could cause serious failures. In addition, the aircraft was especially vulnerable during takeoff and landing. The Allies quickly identified this weakness and began patrolling near known airfields, attacking jets during their most exposed phases. Production never reached the necessary scale. Around 1,400 Me-262s were built, but there were rarely more than 200 operational at any given time. Fuel shortages, bombing of factories, and a lack of trained pilots severely limited its strategic impact. Despite this, the Me-262 managed to destroy hundreds of Allied aircraft. Its psychological effect was immense. It demonstrated that the era of propeller-driven fighters had reached its limit. When the Allies captured intact examples, they began studying them urgently. Engines were disassembled, designs analyzed, lessons immediately applied to their own programs. From this work emerged the first post-war jet fighters. Within a few years, the skies of the world were filled with aircraft that no longer depended on propellers. The Me-262 did not change the outcome of the war. It arrived too late, in insufficient numbers, within a collapsing industrial system. But it permanently changed the future of aerial combat. The STG-44 and the birth of the assault rifle. Before 1943, the concept of an assault rifle did not exist. The world's armies equipped their infantry with two distinct categories of weapons. On one hand, there were bolt-action rifles, long-range, precise and powerful, designed for engagements beyond 800 meters. On the other, there were submachine guns that used pistol ammunition, highly effective at close range, but useless beyond 100 meters. Between these two extremes lay a tactical gap. Most real infantry combat occurred within 300 meters, a range where rifles were too slow and submachine guns too weak. The STG-44 was designed to fill exactly that gap, and in doing so, it permanently changed the nature of modern infantry warfare. When the Red Army entered Berlin in May 1945, Soviet soldiers found something unexpected in abandoned depots and arsenals. Thousands of unfamiliar weapons, unlike the standard Mauser rifles. They were shorter, more compact, with large curved magazines and integrated fire selectors. These weapons could switch between semi-automatic and fully automatic fire. Fully loaded, they weighed just over 5 kilograms. They used an intermediate cartridge, not pistol ammunition, not traditional rifle rounds. It was the Sturmgewehr 44, the STG-44. Development of the weapon began in 1942 under a misleading designation, Maschinenkarabiner 42, automatic carbine. The name was not accidental. Adolf Hitler had explicitly forbidden the development of new infantry weapons, believing Germany should focus on mass-producing existing designs. However, increasingly alarming reports from the Eastern Front painted a different picture. German troops were facing Soviet soldiers armed with the PPSH-41 submachine gun, which in urban combat, trenches and forests delivered overwhelming firepower. The solution was not simply increasing rate of fire. The real problem was ammunition. The standard Mauser cartridge was too powerful for controlled automatic fire. It produced recoil so strong that accurate bursts were impossible. For this reason, engineers led by Hugo Schmeisser developed an entirely new cartridge, the 7.92 by 33 mm known as Kurz short. This round was less powerful than a full rifle cartridge, but far more effective than any pistol ammunition. It allowed controllable automatic fire while maintaining lethal effectiveness out to 300 meters. The STG-44 was designed around that cartridge. It used a gas-operated reloading system in which part of the gases from the fired round drove a piston that cycled the bolt, ejected the spent casing, and chambered the next round. This mechanism was robust and reliable, especially under the extreme conditions of mud, dust, and cold common on the Eastern Front. The fire selector offered unprecedented flexibility. A soldier could fire in semi-automatic mode to conserve ammunition and maintain accuracy, or switch to fully automatic fire to suppress the enemy or dominate an area. This fundamentally changed the way combat was conducted. For the first time, a single infantryman could adapt his weapon to different tactical situations without changing equipment. The STG-44's design also reflected Germany's industrial constraints. In the final years of the war, instead of machining parts from solid steel blocks, stamped sheet metal was used, a faster and cheaper method. The stock and handguard were made of laminated wood, and later models incorporated early plastics. This allowed relatively high production despite Allied bombing. Between 1943 and 1945, more than 400,000 units were produced. When Adolf Hitler learned of the project, he reacted with anger and ordered it halted. However, frontline reports were so favorable that the High Command insisted on continuing production. He eventually approved it on one symbolic but decisive condition. The name had to change. The weapon became the Sturmgewehr, assault rifle. The term, created as propaganda, would define an entire category of weapons for the rest of the century. After the war, its influence was immediate. The Soviets captured factories, blueprints, and large quantities of STG-44s. Although the AK-47 was not a direct copy, it adopted the same core concept: an intermediate cartridge, selective fire, and a high-capacity magazine. In the West, the United States was slower to accept the idea, but eventually developed weapons based on the same principle. Today, the STG-44 is preserved in military museums around the world. Some examples have even reappeared in modern conflicts, still functional decades later. It was not the most advanced weapon of the Third Reich, nor the most visually striking, but it was arguably the most influential. It redefined infantry combat and established a standard that remains in use today. The U-864 and the environmental disaster sleeping on the seabed. In February 1945, off the western coast of Norway, a unique event in naval history took place. A British submarine detected and sank a German submarine while both were fully submerged. The German vessel was the U-864, and its destruction would have consequences that extended for decades. The U-864 was carrying out a special strategic transport mission to Japan. Germany and Japan, allies but geographically separated, relied on long-range submarines to exchange critical materials and advanced technology. The U-864 was transporting technical blueprints, industrial components, specialized personnel, and a particularly dangerous cargo, approximately 67 tons of metallic mercury stored in steel containers. Mercury was a key strategic material. It was used in precision detonators, industrial chemical processes, and specific military applications. Japan lacked sufficient access to it due to the Allied naval blockade, making submarine transport the only viable option. On February 9, 1945, the British submarine HMS Venturer detected the U-864 acoustically while both vessels were submerged. Using only sound-based calculations, the Venturer launched a salvo of 4 torpedoes. One struck, breaking the U-864 in two and sinking it to a depth of approximately 150 meters. It remains the only documented case of a submarine sinking another submarine while both were fully submerged. For decades, the wreck lay on the seabed without special attention. In 2003, Norwegian marine inspections detected mercury contamination in the surrounding sediments. Subsequent investigations located the remains of the U-864 and confirmed that the mercury containers had corroded, releasing the metal into the marine environment. Mercury is highly toxic and bioaccumulates in the food chain. Elevated levels were detected in fish and marine organisms in the area, representing a significant risk to both human health and the environment. Norwegian authorities evaluated several options, including recovering the cargo or sealing the wreck in place. Direct recovery was ruled out due to the high technical risk. The wreck was fragmented, and any disturbance could release even more mercury. Ultimately, the decision was made to encapsulate the wreck under layers of sand, geotextile, and rock, creating a physical barrier to isolate the contaminants. The project was carried out between 2007 and 2020 and continues under permanent environmental monitoring. The case of the U-864 highlighted a less discussed legacy of the war: thousands of wrecks, munitions, and toxic cargoes left at sea that still pose active risks decades later. The submarine had no direct military impact on the conflict, but its sinking resulted in one of the most complex environmental management operations linked to the Second World War. The Nazi Die Glocke and the origin of Wunderwaffe myths. Unlike the previous projects, Die Glocke is not supported by confirmed military documentation or verifiable physical evidence. It is a story that emerged decades after the war and has been repeated and expanded in speculative publications. Its inclusion in this narrative requires a clear distinction between claims and established evidence. The story of Die Glocke appears primarily in a book published in 2000 by Polish journalist Igor Witkowski. The author claims to have accessed transcripts of post-war interrogations of a SS officer in which an experimental bell-shaped device allegedly developed in secret facilities in Silesia was described. According to this account, the device was several meters tall, contained rotating cylinders, and used a substance called Serum 525. It was attributed with effects such as intense radiation, biological damage, and extraordinary physical properties. No original documents, blueprints, photographs, or physical remains supporting these claims have been presented. No Allied archives, including those of scientific intelligence missions such as Operation Alsos, mention any project with such characteristics. There are no records in captured German archives, nor verifiable contemporary testimony from scientists or engineers involved. Nor is there any physical evidence recovered after the war. Some theories link Die Glocke to existing concrete structures in Silesia, particularly a circular construction popularly known as the Henge. However, independent architectural analyses indicate that these structures are consistent with conventional industrial uses, such as cooling tower supports or standard mining infrastructure from the period. The Die Glocke narrative has been amplified by alternative history literature and sensationalist media, where it is attributed functions such as anti-gravity, time travel, or exotic weaponry. From a historiographical perspective, Die Glocke is classified as a modern myth arising within the broader fascination with the so-called Wunderwaffe, wonder weapons, of the Third Reich. Its persistence can be explained by the combination of highly advanced real projects, incomplete documentation, and the absence of clear records for some late-war German programs. Specialists in the history of the Third Reich and the history of technology agree that there is insufficient evidence to consider Die Glocke a real project. Its value lies solely as an example of how gaps in documentation and popular interest can generate narratives that drift away from verifiable facts. Placing it alongside real discoveries is, in itself, illustrative. It shows the difference between history constructed from evidence and history constructed from imagination. Peenemünde and the secret center that gave birth to modern missiles. On May 17, 1945, 9 days after Germany's surrender, a British technical team arrived at Peenemünde on the island of Usedom in the far northeast of Germany. They were not the first to enter the complex. Soviet troops had arrived earlier, removing everything they considered useful. The British, however, came with a very specific objective. They were searching for blueprints, testing equipment, wind tunnels, combustion chambers, and any documentary trace of the projects that had transformed this isolated site into the most advanced weapons development center of the Third Reich. Peenemünde was not unknown to the Allies. It had been bombed 2 years earlier and had long appeared in intelligence reports. Even so, what they found upon entering exceeded what aerial photographs had suggested. It was not a simple testing ground, but a fully integrated scientific and military complex. There were aerodynamics laboratories, liquid oxygen production plants, prototype hangars, a nearly 2-kilometer runway, and launch platforms capable of firing rockets both horizontally and vertically. Everything was designed to research, test, and bring into production weapons with no equivalent in any other country. The site had been chosen in 1936 for practical reasons. Its geographic isolation reduced risk to civilians. Surrounding forests provided natural camouflage, and direct access to the Baltic Sea allowed launches over open water. From the coast, rockets could fly hundreds of kilometers north without crossing populated areas. When Werner von Braun arrived there in 1937 with a small team, the site was little more than a cluster of barracks near a fishing village. Its growth was rapid. By 1943, the complex employed more than 12,000 people, including engineers, technicians, military personnel, and forced laborers assigned to construction tasks. One of the most impressive elements of the complex was its supersonic wind tunnel. In 1940, it was the most advanced in the world. It could simulate speeds of more than 4 times the speed of sound, reproducing the conditions a rocket would experience while passing through the atmosphere at high velocity. When Allied engineers inspected it in 1945, they confirmed that its capabilities exceeded those of any comparable facility in the United States or Britain. At the northern edge of the complex, test stands built on massive concrete blocks supported engines at full power, while sensors recorded thrust, temperature, and vibration. Later British reports emphasized that these stands could handle engines producing far greater thrust than anything the Allies were developing at the time. Peenemünde was not merely testing ideas, it was testing systems close to operational readiness. Between 1942 and 1945, more than 300 A-4 rockets were launched over the Baltic Sea. Early attempts ended in spectacular explosions or unstable trajectories. On October 3, 1942, the first fully successful flight was achieved. The rocket reached more than 80 kilometers in altitude and traveled nearly 200 kilometers before falling into the sea. It was the first time a human-made object reached near space. Allied intelligence closely monitored what was happening there. From 1943 onward, reports from the Polish resistance and aerial reconnaissance missions indicated launch activity and unusual operations. A photograph taken that year clearly showed a rocket standing vertically on a launch pad. The response came in the form of the air raid known as Operation Hydra, carried out on the night of August 17th to 18th, 1943. Hundreds of British bombers attacked the complex in multiple waves, dropping thousands of tons of explosives. The targets were not only technical facilities, but also the scientists and engineers housing. The logic was direct. Knowledge was harder to replace than buildings. The attack caused more than 700 deaths, including the chief engineer responsible for the A-4 engine, and significantly disrupted production. However, it did not destroy the program. Plans, calculations, and key equipment were evacuated to other locations, many of them underground. When British teams walked through the ruins in 1945, they found damaged laboratories, but also revealing documents. There were studies on multi-stage rockets and theoretical designs capable of reaching orbit. In another building, they discovered plans for an intercontinental missile intended to cross the Atlantic. It never progressed beyond the experimental phase, but it demonstrated the scale of the program's technical ambition. After the war, Peenemünde became a contested source of knowledge. The Soviets relocated thousands of German technicians to their territory to rebuild entire programs. The Americans, although arriving later at the site, secured leading scientists and documentation recovered elsewhere. The work carried out at Peenemünde between 1937 and 1945 directly fed into the rocket programs of both superpowers during the Cold War. Today, Peenemünde functions as a historical and technical museum. Among the surrounding forests, launch pads still covered in moss can be seen. Off the coast, the sea preserves the remains of rockets that failed during testing. Operation Bernhard, the largest economic warfare plan in history. During the Second World War, Germany launched one of the most ambitious economic warfare operations ever conceived. It was not based on bombing raids, naval blockades, or industrial sabotage, but on something far more fragile: trust in money. Operation Bernhard was a systematic attempt to destroy the British economy through large-scale counterfeiting of its currency. The plan was initiated in 1942 under the direction of Sturmbannführer Bernhard Krüger, an SS officer. The objective was simple in concept but complex in execution: flood the British financial system with counterfeit pound sterling notes indistinguishable from genuine ones. If the population and financial markets lost confidence in the value of money, the economy could collapse without a military invasion. To carry out the plan, the SS established a secret printing operation inside the Sachsenhausen concentration camp north of Berlin. Around 140 prisoners were selected not for ideology, but for skill. They included professional printers, engravers, chemists, typographers, and experienced forgers. These men were separated from the rest of the camp population and forced to work under the direct threat of execution if they failed. The technical challenge was extraordinary. British banknotes used linen-based paper with complex watermarks, specific inks, and serial numbering with logical patterns. Every element had to be replicated perfectly. The prisoners examined authentic notes under microscopes, identified the chemical composition of the inks, and developed methods to reproduce watermarks by manipulating paper density during production. The greatest challenge was serial numbering. It was not enough for numbers to be unique. They had to follow believable sequences that would not arouse suspicion in banks or commercial circulation. Through statistical analysis, the prisoners succeeded in reproducing plausible patterns. By 1943, the banknotes produced surpassed all known inspection standards. British experts, when examining them after the war, acknowledged that they were virtually indistinguishable from genuine currency. Germany produced around £132 million in counterfeit money, a vast sum for the time. However, the original plan to directly flood the British economy was never fully executed. The reasons remain debated. Fears of economic retaliation, logistical difficulties, and the risk of large-scale detection limited their use. Instead, the counterfeit notes were used as an undercover tool. They were employed to pay agents in neutral countries, finance intelligence operations, and acquire strategic materials on international markets. The fake currency allowed Germany to operate abroad without spending real reserves. As defeat became inevitable, the SS attempted to erase the evidence. Crates filled with banknotes were dumped into alpine lakes along with printing plates and documents. It has been confirmed that large quantities of notes and plates were submerged in Austria's Lake Toplitz in May 1945, and divers have recovered them in later expeditions. Some prisoners were evacuated with the intention of eliminating witnesses, but several survived and testified after the war. Their accounts allowed the operation to be reconstructed in detail. After the conflict, the Allies faced an unexpected problem. Large quantities of counterfeit bills remained in circulation, and it was nearly impossible to identify them with certainty. The Bank of England quietly withdrew certain issues and acknowledged that the damage was irreversible. Operation Bernhard did not destroy the British economy, but it demonstrated that money, as a system based on trust, can be systematically attacked. It was a unique precedent in the history of economic warfare and a case study in the fragility of financial institutions when verification mechanisms are compromised on an industrial scale. The Wolf's Lair, the command center from which the Eastern Front was directed. From 1941 onward, Adolf Hitler's main command center was located at Wolfschanze, Wolf's Lair, a fortified complex built in the forests of East Prussia. It was not a single bunker, but an extensive network of military installations designed to house the political and military leadership of the Reich during operations on the Eastern Front. The complex included more than 80 structures, command bunkers, living quarters, hospitals, power plants, internal railway stations, and anti-aircraft defenses. Hitler's personal bunker was progressively reinforced until its walls reached up to 8 meters of reinforced concrete. The design incorporated multiple structural layers intended to withstand direct hits from heavy bombs. Hitler resided at Wolfschanze for more than 800 days between 1941 and 1944. From there, he directed military campaigns, received frontline reports, and held strategic meetings. The complex operated autonomously with its own power supply, water system, and encrypted communications with Berlin and other command centers. On July 20, 1944, Wolfschanze was the site of the assassination attempt known as Operation Valkyrie. Colonel Klaus von Stauffenberg placed a bomb during a military conference. The explosion destroyed the map room and caused several deaths, but Hitler survived with minor injuries. Structural factors and the bomb's placement under the table reduced its lethality. After the attack, security measures were drastically increased and a massive purge was carried out against both real and suspected conspirators. Thousands were arrested and executed. Wolfschanze continued operating as headquarters until January 1945, when the Soviet advance forced its evacuation. Before withdrawing, German engineers demolished the complex with explosives. When Soviet troops arrived, they found heavily damaged but still recognizable structures. Later, Allied analyses confirmed the scale of the defensive engineering and the resources invested in its construction. Today, the remains of Wolfschanze are a historical site in present-day Poland. Massive fragments of concrete lie scattered through the forest, silent evidence of the defensive paranoia of a regime that mistrusted every shadow. The V3 and the gun that tried to bombard London from continental Europe. In mid-1943, the German High Command approved a project unlike any other weapon under development. It was not an aircraft, a rocket, or a guided missile. It was long-range fixed artillery designed to continuously bombard London from continental Europe. The weapon received several technical designations, but it would eventually be known as the V3, the third retaliation system of the Reich. The core of the project was an exceptionally long gun. Each barrel would measure approximately 130 meters in length and would be permanently installed inside tunnels excavated into a limestone hill near Mimoyex in northern France. Unlike a conventional cannon, the V3 incorporated multiple auxiliary combustion chambers distributed along the barrel. These chambers contained secondary explosive charges that were intended to detonate sequentially as the projectile traveled down the tube, progressively increasing its velocity. The projectile itself was 150 millimeters in caliber and weighed about 140 kilograms. According to German calculations, the system would achieve speeds exceeding 1,500 meters per second, with a theoretical range of up to 165 kilometers. This would make it possible to strike London directly from northern France. The full plan called for the installation of 50 guns at Mimoyex, organized into several underground batteries. If the system had functioned as intended, each barrel could have fired dozens of projectiles per hour, enabling sustained bombardment over long periods. The construction of the facility began in 1943 under the supervision of the organization Todt, using thousands of forced laborers. Inclined tunnels were excavated, reinforced with massive volumes of reinforced concrete, and fitted with electrical systems, ventilation, and internal access routes for ammunition and personnel. The complex was buried beneath dozens of meters of rock. The Allies identified Mimoyex as a priority target within the crossbow campaign aimed at neutralizing long-range weapons. In July 1944, British Lancaster bombers attacked the site using tallboy bombs, large munitions designed to penetrate deep into the ground before detonating. Several explosions caused internal collapses, destroyed tunnels under construction, and inflicted heavy casualties among the workers. Although the facility was not completely destroyed in a single raid, the structural damage prevented further construction. The V3 was only used in a limited form. In late 1944, smaller versions of the gun, about 50 meters long, were installed near Lamperden in German territory. From there, approximately 180 shells were fired at the city of Luxembourg. The results were technically poor. Accuracy was very low, with scattered impacts, and many projectiles failed mid-flight due to stabilization issues. Post-war Allied analysis concluded that the V3 was not viable as a strategic weapon. The system's complexity, structural vulnerability, and poor real-world performance made it militarily inefficient. The program was permanently cancelled following the Allied occupation of the area. The Riese project and the colossal engineering beneath the Silesian mountains. Between 1943 and 1945, Germany initiated one of the largest underground construction programs of the entire war in the mountains of Silesia, a region that was then under German control. The project, known as Riese, Giant, consisted of an extensive network of tunnels, galleries, and chambers excavated directly into solid rock, distributed across several separate but interconnected sites. The project included at least 7 main complexes, among them Ossowka, Wodas, Rzeczka, and Soboń, located within a relatively small radius around the present-day Polish town of Wałbrzych. Each complex contained large main tunnels, side galleries, and vertical shafts, some reinforced with thick layers of reinforced concrete. In certain sections, double railway tracks were installed, indicating that continuous transport of materials or personnel had been anticipated. The exact purpose of Riese was never conclusively documented. German records were destroyed or evacuated before the retreat, and the files captured by the Soviets did not provide a definitive answer. The main hypotheses point to three possible uses: a large underground headquarters, bomb-proof industrial facilities, or a combination of both. Physical evidence suggests that the objectives of the project changed several times during construction, reflecting Germany's rapidly deteriorating military situation. Construction was carried out almost entirely using forced labor. Tens of thousands of prisoners, mostly from the Gross-Rosen concentration camp, were used for excavation, rock transport, structural reinforcement, and concrete pouring. Conditions were extreme. Ventilation was poor, dust constant, humidity high, and low temperatures combined with endless working hours resulted in a very high mortality rate. Conservative estimates place the number of deaths between 5,000 and 13,000 workers, although the exact figure cannot be determined with certainty. From a technical standpoint, Riese demonstrates substantial engineering capability. Some tunnels reach several meters in height and width, sufficient for vehicle traffic. The main chambers feature vaulted ceilings designed to distribute the load of the overlying rock strata. In several areas, drainage systems and channels for groundwater are visible, indicating long-term planning considerations. However, by the end of the war, only a fraction of the project had been excavated, and virtually no sections had been fitted with machinery, full electrical wiring, or operational infrastructure. There is no evidence of industrial production or of use as an active command center. The project was abandoned before it could fulfill any concrete military function. In practical terms, it represented a massive investment of human lives and material resources that yielded no operational return. After the war, Soviet authorities inspected the tunnels in search of technology, archives, or valuable materials. Nothing of significant value was recovered. For decades, parts of the complex remained closed or under military control. In more recent times, several sections have been opened to the public as historical sites. The unfinished labyrinth remains for visitors a disturbing reminder of the scale of what the Third Reich was capable of building and of what that effort cost in human terms. Mittelwerk and Dora, advanced technology and industrial slavery under the mountain. On April 11, 1945, the 104th Infantry Division of the United States Army liberated the Dora-Mittelbau concentration camp near Nordhausen in central Germany. What they found was unlike any camp seen before. It was not just barracks surrounded by barbed wire, but the entrance to an extraordinary underground industrial complex. Two parallel tunnels, nearly 2 kilometers long each, excavated into the Kohnstein mountain, were connected by 46 cross galleries. Beneath 20 meters of solid rock lay Mittelwerk, the factory where V-2 rockets had been produced. The first American soldier to enter described a scene difficult to comprehend. Railway tracks ran through the tunnels, large cranes hung from the ceiling, and assembly lines disappeared into the darkness. Thousands of rocket components lay scattered alongside abandoned machinery. But what struck most was not the technology, it was the smell. A harsh, acrid stench came from hundreds of corpses piled near the entrances, prisoners who had died during the final days of evacuation. Deeper inside, survivors were found, skeletal figures in striped uniforms, many unable to walk, who had spent months working underground. Mittelwerk was not originally conceived as an underground factory. Until 1943, V-2 production had been concentrated in Peenemünde in surface facilities. On August 17, 1943, the Royal Air Force launched Operation Hydra, a massive raid that destroyed laboratories, workshops and living quarters, killing 735 people. Hitler ordered that all critical installations be dispersed and moved underground. The Kohnstein mountain was chosen for strategic reasons. Tunnels had already been excavated in the 1930s for fuel storage. The rock was strong enough to withstand direct bombing, and the location was beyond the effective reach of Allied escort fighters. But building a complete underground factory in a matter of months required a labor force that could not refuse or resist. Between August 1943 and March 1944, more than 10,000 prisoners were transferred to Dora-Mittelbau, most of them from Buchenwald. Their initial task was to excavate galleries and adapt existing tunnels. They worked with picks, shovels, and explosives in inadequate ventilation. Rock dust filled the air and destroyed their lungs. Blasts caused frequent collapses. During the early months, prisoners slept inside the tunnels themselves on wooden bunks stacked in multiple levels, without heating or natural light. The living conditions were designed for extreme depletion. Latrines were insufficient. Water was scarce. Food rations were deliberately calculated below the minimum required for survival. Work shifts lasted up to 18 hours. Beatings were routine. Any sign of exhaustion was interpreted as sabotage. Death became a structural element of the system, not an accidental consequence. Field records analyzed in later trials indicate that approximately 60,000 prisoners passed through Dora-Mittelbau between 1943 and 1945. At least 20,000 died. The main causes were malnutrition, extreme exhaustion, respiratory diseases caused by rock dust, and executions for real or alleged sabotage. Statistically, survival in Dora-Mittelbau was less likely than death before liberation. Meanwhile, underground V2 production advanced with industrial logic. Each rocket passed through 42 workstations. In one gallery, fuel tanks of ethanol and liquid oxygen were assembled. In another, the engine and combustion chamber were installed. Further along, guidance systems with precision gyroscopes were fitted. Finally, the warhead, containing nearly a ton of amatol explosive, was attached. The entire process was supervised by German civilian engineers and overseen by the SS. The contradiction was extreme. The V2 was a machine of extraordinary precision. Its engine had to withstand temperatures approaching 2,700 degrees Celsius. Injection systems operated within hundredth of a millimeter tolerances. Gyroscopes had to be perfectly balanced. Yet much of the assembly was carried out by men who were malnourished, who had not received adequate protein intake for weeks, and who worked under constant threat. This created a problem the system never managed to eliminate: passive sabotage. It was not necessary to visibly destroy parts. It was enough to tighten a bolt with insufficient torque, perform a poor secondary weld, or leave a connection slightly loose. Post-war Allied analyses suggest that up to 30% of V2 rockets launched failed due to technical issues. Part of this was inherent complexity. Another part was deliberate sabotage, which could not be eradicated without eliminating the workforce itself. After liberation, the Allies documented the system of terror. They found punishment chambers where prisoners were suspended from beams with their arms tied behind their backs, a form of torture that dislocated shoulders and caused progressive suffocation. They discovered improvised crematoria used to incinerate bodies and prevent epidemics. Medical reports from survivors described extreme cases of scurvy, advanced tuberculosis, starvation edema, and gangrene. But liberation coincided with another priority. American technical teams arrived with clear orders to inventory, dismantle, and transport anything of technological value. While survivors were being treated in field hospitals, components, tools, and documentation were catalogued. Everything that could be moved was shipped to the United States before the area fell under Soviet control in July 1945. This created a profound moral tension. The same rockets that had killed civilians and been built through slave labor became the foundation of the American space program. Werner von Braun, the technical director of the V2 program, who had visited Mittelwerk repeatedly while being fully aware of the conditions there, was taken to the United States, granted citizenship, and went on to direct the development of the rocket that sent humans to the moon. For decades, that contradiction was minimized. Von Braun was presented as a visionary rather than as part of a system of industrial slavery. It was only with the opening of archives and survivor testimony in the late 20th century that a more complete picture emerged. In 1984, Arthur Rudolph, another key engineer from Mittelwerk, left the United States after investigations were launched into his role at Dora. NASA revoked all his awards and honors. At the agency, he had directed the development of the Saturn V rocket. The history of Dora-Mittelbau is the history of modernity in its darkest form, humanity's ability to build technological marvels on mountains of deliberate suffering, and the difficulty of separating scientific legacy from the moral legacy that comes with it.